C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 1. Let's discuss Chapter 1, Cloud versus Local, Privacy, Latency, and Cost. Turning our attention to theoretical foundations. The transition from cloud-centric AI architectures to local edge AI represents a fundamental paradigm shift in how we conceptualize, deploy, and interact with intelligent systems. To understand this shift, we must dissect the three pillars that govern this decision: privacy, latency, and cost. While cloud services offer the allure of infinite scalability and zero-maintenance hardware, they introduce a dependency on external infrastructure that often conflicts with the constraints of real-world applications. Local inference, particularly using frameworks like ONNX Runtime and languages like C#, empowers developers to reclaim sovereignty over their data and execution environment. Turning our attention to the privacy and sovereignty paradox. In the cloud model, data privacy is a matter of trust. When you send a prompt to a hosted large language model, LLM, like GPT-4, you are effectively shipping your intellectual property, user inputs, proprietary code, or sensitive documents, across the public internet to a data center owned by a third party. Even with strict terms of service and encryption in transit, the data exists in a memory buffer on a remote server, subject to the provider's policies, potential breaches, and jurisdictional laws. Local inference flips this model entirely. By running a model like Phi 3 or Llama 3 directly on the user's machine or an edge device, the data never leaves the local boundary. This is not merely a technical implementation detail, it is a compliance and architectural necessity for industries like healthcare, finance, and defense. Analogy: the bank vault versus the cloud safe. Imagine you have a valuable document. The cloud approach is akin to renting a safe deposit box in a bank. You trust the bank's security guards, cameras, and vaults. However, every time you need to view the document, you must travel to the bank, present identification, and access it under their surveillance. The local approach is buying a high-quality safe for your own office. You hold the only key. You have immediate access, and no one else can see the contents, but you are solely responsible for the safe's physical integrity and the security of the room it resides in. In C# development, this architectural decision is often abstracted through dependency injection, DI, and interface segregation. We previously explored in Book 8, Microservices and API Integration, how to design ILLM client interfaces to communicate with cloud endpoints. To pivot to local inference without rewriting the entire application, we leverage the same interface but swap the implementation. Here, we're defining an interface named iText Generation Service. This is a crucial architectural decision. Interfaces in C# define a contract. Any class that implements this interface promises to provide a specific set of methods. In our case, this interface guarantees that any text generation service, whether it's running locally or in the cloud, will have a generate-async method that takes a string prompt and returns a task string. This abstraction is vital for decoupling our application logic from the specific implementation details of a text generation provider. It allows us to swap out different AI models or services without changing the core application code, promoting flexibility and maintainability. Imagine we start with OpenAI, but later want to switch to Llama 3 or a custom local model. This interface makes the transition seamless. Now, observe how we provide a concrete implementation of our iText Generation Service interface with the OpenAI Service class. This class effectively fulfills the contract defined by the interface. The generate-async method, as indicated by the comment, would typically encapsulate the logic for making an HTTP call to the OpenAI API. This design choice clearly separates the concerns. The interface defines what a text generation service does, and OpenAI service defines how OpenAI specifically does it. This separation is a cornerstone of good software design, making our code more modular, testable, and easier to understand. If we later introduce a local Llama service, it would also implement iText Generation Service, but its generate async would involve local ONNX Runtime calls, not HTTP requests. In the context of Edge AI, we implement this interface locally. The consuming application remains agnostic to the source of the intelligence, allowing a seamless transition between cloud and local based on configuration or availability. Here, we're defining a class called ONNX Service. This class is designed to provide text generation capabilities, as indicated by its implementation of the iText Generation Service interface. The comment on line 1, / local implementation using ONNX Runtime, immediately tells us the core technology this service leverages, ONNX Runtime. This is a crucial architectural decision. By using ONNX Runtime, we're opting for a highly optimized, cross-platform inference engine that can execute pre-trained machine learning models. The primary benefit here is performance. ONNX Runtime is engineered for efficiency, often outperforming raw framework-specific inference engines. The class is declared public, making it accessible throughout our application. Notice the generate async method, which is an asynchronous method returning a task string. This is a best practice in modern C# applications, especially when dealing with potentially long-running operations like AI inference, as it prevents blocking the calling thread and keeps the application responsive. The comment on line 7, / the data never leaves the process memory, highlights a significant security and privacy advantage of this local approach. Unlike cloud-based AI services where data is transmitted over networks, here, all processing happens within the application's memory space, which is ideal for sensitive data or environments with strict data residency requirements. This design choice is fundamental for applications where data privacy and low-latency inference are paramount. This architectural pattern is crucial because it decouples the policy, where data lives, from the mechanism, how text is generated. Turning our attention to latency, the speed of light and the speed of queues. Latency in AI is often misunderstood. It is not solely the time it takes for the GPU to perform matrix multiplications, it is the sum of the entire pipeline. 1. Network latency, the physical distance between the client and the data center. Light travels approximately 300,000 kilometers per second in fiber, but routing, handshakes, TCP/TLS, and load balancers add milliseconds. 2. Queue latency, cloud providers operate massive fleets. Your request enters a queue. During peak times, rate limits are essentially queue positions. 3. Processing latency, the actual inference time. Local inference eliminates the first two. The network is the system bus, PCIe, and the queue is the OS thread scheduler. For interactive applications, e.g., real-time code completion in an IDE like Visual Studio, these saved milliseconds are the difference between a fluid experience and a frustrating lag. Analogy, the restaurant versus the home kitchen. Ordering from a cloud API is like ordering takeout. It might be delicious and prepared by a master chef, a massive GPU cluster, but you have to wait for the delivery driver, network latency. If the restaurant is busy, rate limiting, your order sits on the counter. Cooking at home, local inference, means you might have a smaller oven, consumer GPU or CPU, but you start cooking the moment you decide to eat, and the food is on your plate instantly. Turning our attention to total cost of ownership, TCO infrastructure versus development. The financial model of cloud AI is operational expenditure, OpEx. You pay per token or per millisecond of compute time. While this eliminates upfront hardware costs, it creates a variable expense that scales with usage. For high-volume applications, this can become exorbitant. Local inference shifts this to capital expenditure, CapEx. You buy the hardware once, a GPU, a NUC, or an industrial PC. The marginal cost of running an additional inference is near zero. However, this introduces a development cost. You must optimize the model for the specific hardware, manage memory, and handle driver compatibility. The hardware threshold. The viability of local inference is defined by the hardware threshold. Modern CPUs with AVX512 instruction sets and NPUs, neural processing units, are making local inference viable even without discrete GPUs. ONNX Runtime is the linchpin here, as it provides a unified accelerator interface, execution providers, that abstracts the hardware differences between CUDA, DirectML, CPU, and OpenVINO. Let's discuss the role of C# and ONNX in local inference. C# has evolved into a first-class language for AI workloads, bridging the gap between high-performance systems programming and rapid application development. The .NET ecosystem's interoperability with ONNX Runtime is robust, allowing developers to load models, export it from PyTorch or TensorFlow, and run them with minimal overhead. ONNX, Open Neural Network Exchange, is the standard format that enables this interoperability. It acts as a universal translator. A data scientist trains a model in Python, exports it to ONNX, and a C# engineer consumes it in a .NET application. In C#, we utilize the Microsoft.ml.ONNX Runtime namespace. The core architectural component is the inference session. This class represents the loaded model and the execution environment. It manages the lifecycle of the model, memory allocation, and the underlying execution provider, e.g., DirectML for Windows GPUs. Analogy, the universal power adapter. Imagine a model trained in Python is a device with a proprietary plug. ONNX is the universal adapter that converts that plug to a standard socket. C# and the ONNX runtime provide the electricity, the execution engine. Whether you plug into a wall outlet, CPU, or a high-voltage industrial socket, GPU, the device runs. Now, let's talk about theoretical foundations. To understand how this works in practice, we must visualize the flow of data from a C# application to the ONNX runtime and back. 1. Input processing. The application takes a string, prompt. This string must be tokenized, converted into numerical IDs that the model understands. In cloud APIs, this is hidden. Locally, we often need to handle tokenization explicitly, though libraries like Microsoft.ml.ONNX Runtime, transformers assist. 2. Session creation. We instantiate an inference session pointing to the .onx model file. We configure session options to select the execution provider, e.g., execution provider, DML for DirectML. 3. Binding inputs. We create an ORT value, a wrapper around native memory, for the input IDs. This requires careful memory management to avoid leaks. 4. Inference. We call session, run. The runtime takes the input tensors, executes the graph operations on the selected hardware, and produces output logits. 5. Post-processing. The logits are processed, e.g., via softmax, to select the next token. This is often done in a loop for text generation, autoregressive decoding. The following diagram illustrates this pipeline. The diagram illustrates an autoregressive decoding loop where the model processes the current context to output a probability distribution via softmax, which is then used to select the next token that is appended back to the input for the subsequent iteration. Let's discuss the what-if edge cases and constraints. While local inference offers control, it introduces constraints that cloud services abstract away. 1. Memory management and quantization. Large models, 7B+ parameters, require significant VRAM/RAM. A full precision, FP32, 7B model requires 28 GB of memory. This is impractical for most consumer hardware. This necessitates quantization, reducing the precision of the weights, e.g., to INT8 or FP16. In the C# context, we must ensure the ONNX model is quantized correctly. If the hardware does not support INT8 operations, the runtime might dequantize on the fly, impacting performance. 2. The cold start problem. Cloud APIs are always warm. Locally, loading a 4 GB model from disk into memory can take seconds. This is the cold start. In C#, we mitigate this by keeping the inference session alive as a singleton service within the application's lifecycle. We do not dispose of it until the application shuts down. 3. Hardware heterogeneity. A C# application running on a developer's laptop, NVIDIA GPU, must also run on a client's office PC, Intel integrated graphics, or an industrial edge device, ARM CPU. This is where the execution provider abstraction is vital. We can dynamically select the provider based on availability. Here, we're importing the Microsoft.ml.ONNX Runtime namespace. This is the foundational library that allows us to load and execute ONNX, Open Neural Network Exchange, models. Think of it as the engine that powers our local AI inference. Without this, we wouldn't be able to interact with our pre-trained models. We instantiate session options here. This object is crucial because it acts as a configuration hub for our ONNX inference session. It's where we'll specify various settings, most importantly, which hardware acceleration provider ONNX Runtime should use. This decision significantly impacts performance, as you'll see shortly. This comment, while brief, highlights a critical architectural decision: prioritizing hardware acceleration. When we're running large language models, LLMs, or other complex AI models, the computational demands are immense. Leveraging specialized hardware like GPUs can reduce inference times from minutes to seconds or even milliseconds, making real-time applications feasible. We start by checking for the availability of DirectML. DirectML is Microsoft's low-level API for hardware-accelerated machine learning on Windows. It's particularly beneficial because it can leverage a wide range of GPUs, including those from AMD, Intel, and NVIDIA, often providing a more unified experience on Windows platforms. We prioritize it because for many Windows users, it's the most accessible and often performant option. If is DirectML available, returns true, we append the DirectML execution provider to our session options. The append execution provider _DML, 0, call tells ONNX Runtime to use the first available DirectML device, index 0. This is a direct instruction to offload the heavy computational tasks of our neural network to the GPU, dramatically speeding up inference compared to CPU-only execution. The T0 often refers to the primary GPU in a multi-GPU setup. If DirectML isn't available, our next best option is CUDA. CUDA is NVIDIA's parallel computing platform and API model, specifically designed for NVIDIA GPUs. It's incredibly powerful and widely adopted in the AI community. We check for its availability next because if a user has an NVIDIA GPU, CUDA is usually the most performant way to utilize it for AI workloads. Should is CUDA available be true, we instruct ONNX Runtime to use the CUDA execution provider. Append execution provider _ CUDA 0 directs the session to utilize the first detected NVIDIA GPU. This is a highly optimized path for NVIDIA hardware, offering superior performance for complex models. The choice between DirectML and CUDA depends on the operating system and the specific GPU hardware present, but both aim to maximize hardware acceleration. This else block represents our fallback strategy. If neither DirectML nor CUDA, meaning no suitable GPU acceleration, is detected, we must ensure our application can still run, albeit with potentially slower performance. Robust applications always account for scenarios where optimal hardware isn't present. Here, we append the CPU execution provider. This is the most universal option, as every system has a CPU. The comment // fallback to CPU with AVX optimization is important. Modern CPUs often include extensions like AVX, advanced vector extensions, that can significantly speed up mathematical operations, which are common in AI models. ONNX Runtime CPU provider is usually compiled with support for these optimizations, making it as efficient as possible when GPU acceleration isn't an option. While slower than GPU, it guarantees the model can still be run. Finally, after configuring our session options to prioritize the best available hardware, we create an inference session. We pass the path to our ONNX model file, model.onx, and the session options we just prepared. This inference session object is now ready to load the model and perform actual predictions. It encapsulates the model graph, its weights, and the chosen execution provider, effectively setting up the environment for running our AI model. This is the pivotal step where the model becomes operational within our application. This logic ensures the application degrades gracefully. It is the developer's responsibility to handle the performance delta between these providers, unlike cloud APIs where the provider guarantees a specific latency SLA. Now, let's explore conclusion. The theoretical foundation of edge AI with C# and ONNX rests on the trade-off between autonomy and convenience. By moving inference locally, we gain privacy, deterministic latency, and long-term cost savings. However, we inherit the burden of hardware management, memory optimization, and model maintenance. The architectural pattern of using interfaces, like iText Generation Service, allows us to navigate this trade-off dynamically, creating systems that are resilient, private, and performant. This chapter sets the stage for the technical implementation where we will turn these theories into compiled, executable C# code. Let's discuss basic code example. Let's model a simple sentiment analysis task. Imagine you are building a smart inbox feature that needs to instantly categorize incoming user feedback as positive or negative without sending that potentially sensitive feedback to a cloud server. We will use a distilled version of the Phi-3 model exported to ONNX format to perform this local inference. Here is the complete, self-contained C# console application. Here, we're setting up our project by including necessary using statements. Notice lines 8 and 9, Microsoft.ml.onx runtime and Microsoft.ml.onx runtime, tensors. These are absolutely crucial because they provide the core functionalities for interacting with ONNX, Open Neural Network Exchange, models. ONNX is an open standard that defines a common set of operators and a common file format to represent deep learning models. This allows us to train a model in one framework, like PyTorch or TensorFlow, and then deploy it efficiently using ONNX runtime in a different environment, like our C# application. This decoupling of training and inference environments is a powerful architectural choice, offering flexibility and often better performance for deployment, especially on edge devices or CPUs where Python dependencies might be heavy or unavailable. Without these using statements, our C# code wouldn't know how to load, run, or interpret the outputs of our Phi-3 model. We begin by defining our local Phi-sentiment namespace, line 11, and the program class, line 13, which contains our application's entry point, the main method, line 15. Inside main, at line 20, we declare a user feedback string. This string, the new update completely drains my battery. I hate it. Represents the input we want our Phi-3 model to analyze. In a real-world application, this input wouldn't be hard-coded, it would dynamically come from user interfaces, databases, or API calls. For instance, imagine a mobile app collecting user reviews or a customer support system processing tickets. We're simulating that dynamic input here to demonstrate the inference process. This initial step highlights the practical application of our model, taking raw text and preparing it for AI processing. Next, we define the model path at line 26. This is a critical configuration step, pointing to where our pre-trained Phi-3 ONNX model file resides on the local disk. Notice the comment on line 23, you must download this model separately. This is a common pattern in Edge AI. Models are often too large to be bundled directly with the application source code and are typically downloaded as assets. We're specifically using a quantized version, e.g., CPU, int4, RTN, block, 32, ACC, level, 4.onx. Quantization is a technique that reduces the precision of model weights, e.g., from 32-bit floating point to 4-bit integers, significantly decreasing model size and improving inference speed, especially on resource-constrained devices like CPUs or mobile phones. This choice has major implications for performance and memory footprint, making local inference feasible. Lines 28 to 30 are simply for user feedback, printing out what input is being processed and which model is being used, which is good practice for debugging and user experience. The try-catch block starting at line 32 is essential for robust error handling. Running inference with large models can encounter various issues, such as missing model files, corrupted files, or out-of-memory errors. The try block encapsulates the core logic, while the catch block, lines 101 to 107, will gracefully handle any exceptions, preventing the application from crashing and providing informative messages. At line 37, we initialize an inference session using new inference session, model path. This is where the ONNX runtime loads the model's computational graph and weights from the specified .onx file into memory. The using statement here is vital. It ensures that the inference session object, which consumes significant system resources, memory, potentially file handles, is correctly disposed of once it goes out of scope. This prevents resource leaks and is a best practice for managing unmanaged resources in C#. Lines 39 to 51 deal with the crucial step of preprocessing, tokenization. Large language models, LLMs, like Phi-3 don't directly process human-readable text. Instead, they operate on numerical representations called tokens. A tokenizer's job is to convert text into a sequence of these token IDs. Imagine mapping words or subword units to unique numbers. Here, we're simulating this process. Line 45 shows the specific prompt format Phi-3 expects, user. Prompt end. Assistant. This is a common pattern for instruction-tuned models, providing clear delimiters for different roles in a conversation. While a real application would use a sophisticated tokenizer library, as noted in line 47, for this example, we're using mock tokenizer encode, line 50, to simplify the demonstration. This highlights that the quality and correctness of tokenization directly impact the model's ability to understand and respond appropriately. Incorrect tokenization can lead to nonsensical outputs or misinterpretations by the LLM. At lines 53 to 64, we're preparing the input for the ONNX runtime. LLMs expect their input as tensors, which are multidimensional arrays of numbers. Line 55 creates a dense tensor long from our input token IDs. The long type is used because token IDs can sometimes exceed the range of int, especially with larger vocabularies. The shape, 1, input token IDs, length, is critical. 1 represents the batch size, we're processing one input sequence at a time, and input token IDs, length is the sequence length, the number of tokens in our prompt. This shape is standard for many transformer models. Lines 59 to 63 then create a list named onx value. This is how ONNX runtime receives its inputs, a collection of named tensors. Session.input metadata, keys, first, line 60, dynamically retrieves the expected input name from the loaded ONNX model, typically input_IDs for LLMs. This makes the code more robust, as it doesn't hardcode the input name, adapting to different models if needed. This step is about bridging the gap between our C# data structures and the ONNX model's input expectations. Line 68, using var results equals session, run, inputs, is the heart of the inference process. This is where the ONNX runtime takes our prepared input tensors, feeds them through the loaded Phi-3 model's computational graph, and performs all the matrix multiplications and activations necessary to produce an output. This is the heavy lifting as mentioned in the comment. The using statement here is again crucial for resource management, ensuring that the results object, which holds the model's output tensors, is properly disposed of after use. After the model runs, at line 73, we extract the output tensor using results, first, .astensor float. LLMs typically output logits, which are raw, unnormalized scores for every possible token in the model's vocabulary. These scores indicate how likely each token is to be the next token in the sequence. The float type is standard for these raw scores. Understanding this output is key to post-processing and generating human-readable text. Lines 79 to 99 handle post-processing and decoding the model's output. The getTopToken method, line 76, is called to find the token ID with the highest logit score. This is a simple, greedy decoding strategy, meaning we always pick the most probable next token. While effective for demonstration, more advanced strategies like beam search or top K sampling are used in real-world applications to generate more diverse and coherent text. The loop from lines 85 to 97 simulates text generation. In a full LLM generation pipeline, the newly predicted token would be appended to the input sequence, and the model would be run again in an autoregressive fashion to predict the next token, building up a response word by word. For simplicity, we're just decoding and printing the first predicted token, then breaking if an end token is predicted. This demonstrates the fundamental cycle of LLM inference: tokenize input dash, run model dash, get logits dash, decode token dash, repeat. The console.foreground color changes, lines 82, 98, are purely for visual clarity, making the model's output stand out. This catch block, lines 101 to 107, is our safety net. If any exception occurs during the execution of the try block, control immediately transfers here. For example, if the model path, defined on line 26, is incorrect, or the ONNX model file is corrupted, an exception will be thrown by the inference session constructor. Instead of crashing, the application will print a user-friendly error message in red, lines 103 to 105, and provide troubleshooting advice, line 106. This is crucial for user experience and debugging, especially in scenarios where users might forget to download model assets or misconfigure paths. It demonstrates robust application design by anticipating potential failures and guiding the user towards a solution, rather than presenting a cryptic error or simply terminating. Now we move to our helper methods, starting with mock tokenizer encode at line 112. This method is a simplified stand-in for a real tokenizer. Remember, LLMs work with numbers, not text. A true tokenizer would typically load a vocabulary file, like a tokenizer.json or vocab.txt, and apply complex rules, like byte pair encoding or word piece, to break text into subword units and map them to integer IDs. Our vocab dictionary, lines 117 to 122, manually maps a few specific words and special tokens, like user, to arbitrary integer IDs. This is a gross simplification but serves to illustrate the concept of tokenization. Look at lines 125 to 133, we split the text by spaces, then look up each word in our mock vocabulary. If a word isn't found, we assign a generic unknown token ID, line 132. This highlights the importance of a comprehensive vocabulary. A real tokenizer would handle out-of-vocabulary words much more gracefully, often by breaking them into known subword units. This method is crucial for making our demonstration self-contained without requiring a full tokenizer library setup. The mock tokenizer decode method, lines 137 to 150, is the inverse of mock tokenizer encode. After the model predicts a token ID, we need to convert that ID back into human-readable text. Again, this is a highly simplified version of a real tokenizer's decoding process. A true decoder would use the same vocabulary file as the encoder and reconstruct the text, often handling special tokens, like hashtag 4 subwords, and whitespace correctly. Here, we're using a series of if statements to map specific token IDs back to corresponding words or special strings. For instance, 32,000 maps to an empty string, representing an end-of-sequence token, and 452 maps to it. This method is primarily for demonstrating the final step of the LLM pipeline, taking the model's numerical output and presenting it in a comprehensible format to the user. Without this decoding step, the model's output would just be a stream of numbers, which isn't very useful to us. Finally, we have the getTopToken method, lines 152 to 176. This method is responsible for interpreting the raw output of our LLM. Remember, the model outputs logits, a large array of scores for every possible token in its vocabulary. The tensor's shape is typically batch size, sequence length, vocabulary size. We are interested in a prediction for the next token, which corresponds to the last position in the sequence length dimension. Line 159 calculates vocab size, which is the size of the model's vocabulary, the number of unique tokens it knows. Line 160 is key, it calculates the last token offset to find the starting index of the logits for the final token in the input sequence. This is because the model predicts the next token based on the entire sequence fed so far. The loop from lines 165 to 174 then iterates through these logits for the last token, finding the token ID, max index, that has the highest score, max val. This greedy approach is the simplest way to select the most probable next token. In essence, this method translates the model's raw numerical probabilities into a single, concrete token prediction, which can then be decoded into text. By scanning this qrcode you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. Thank you for watching. Thank you for your attention. This lesson is excerpted from Volume 9, Chapter 1 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all the details here, https://github.com/edgarmilvis/C# programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.